Hey everyone, just a quick intro to tell you that this video is actually a replay. It's actually the video from my talk at Black Hat USA this year, and the talk is about Fuzzing WebAssembly VM. So you have the link to the slides directly just below, and please enjoy the video and let me know what you think about that, and if you want to see more video like this one. Thank you.
So, welcome in this talk. As the name suggests, we're going to discuss about fuzzing. So, it's a journey into fuzzing WebAssembly virtual machine. So, it will be mainly focused on the different steps you need to do in order to do fuzzing when you are targeting a huge and complex target, that is in that case the WebAssembly virtual machine. So, of course, we found bugs. I will not discuss too much about them and even less about exploitation. It's really more focused on fuzzing, and I hope you will find a lot of interesting points to apply that on other targets. So my name is Patrick. I'm the founder and CEO of Fuzzing Labs. So as the name suggests, we are doing fuzzing and vulnerability research. So mainly on, I would say, different targets, and the main goal for us is really to develop further custom fuzzer and also custom security tool. So the main focus we are doing is mainly Rust, Go, and browser fuzzing in general. So a quick introduction to WebAssembly. So WebAssembly has been introduced in 2017 officially with the MVP 1.0. It's a binary instrumentation in binary instrumentation format, instruction format, but it's just not a binary format. It's a binary format plus a text-based representation plus a stack-based virtual machine. That means a complete architecture as itself. So it's natively supported by all the major browsers since quite some time now. And the main goal of WebAssembly is basically not to replace JavaScript, is to be in addition to JavaScript in order to be more fast and so on. So how WebAssembly works. Basically, you have two steps. The first one is basically the compilation. So you have your classical piece of source code, and you will compile that into WebAssembly. It will be your compilation target. So there is some tools like LLVM that actually support WebAssembly as a target, and Script10, BinaryM, and some others. So at the end, you have something like that, like the Fibonacci function in C, C++, or Rust, and you're going to compile that into the binary files that is the WebAssembly module. On the other part, you have the runtime and host environment. So your WebAssembly VM that will actually take as an input a WebAssembly module will decode and execute the module. You have the most famous one, let's say, is V8 that actually contain a WebAssembly virtual machine. And you have also like Wasmer and Wasruntime that are actually pretty famous. So the way it works when you are providing a WebAssembly module, it will go to multiple stages. So the first one is the decoding and the parsing. So from this binary format, the WebAssembly VM will actually create an internal module representation. Then it will do the validation phase, meaning that it will decode the module and check for particular stuff like type checking and some others. Then you have the instantiation. Basically, it will create a module instance and it will create some additional stuff. So you can think of memories, globals, tables, and some others. So that's basically a quick overview of the VM and the host interaction and different objects. So in one side, on the top, you have a bunch of memories, a bunch of globals and tables. Those ones are created by the host. And basically, those ones will be shared to the WebAssembly instance that is at the bottom. The WebAssembly instance is actually immutable, meaning that once the WebAssembly module is loaded and instantiated, there is no way to modify the function body, the function content, the indirect function table, and the execution stack. It's not a classic stack. I mean, it's a stack for like you just push and pop some data on it, so it's kind of really limited in that way. So that's why we are telling that actually WebAssembly is sandboxed. That's typically for this kind of reason. Finally, once the WebAssembly module is ready to go, you have the execution, and in that case, the host will maybe provide some argument to a specific function that will be exported, and then it will run the WebAssembly module, the specific bytecode of WebAssembly, and do the job. So in terms of, so that's just the WebAssembly VM, and of course this WebAssembly VM will need a host environment. So usually we are speaking about browsers like what I've done at the beginning, but it's not the only host that is actually running WebAssembly VM. One other case is basically blockchains that can use WebAssembly VM for like smart contracts in general, and there is plenty of other ones. For standalone VM, so that's this case, so you can think of a WebAssembly VM that is running on a server. You can think of edge computing, IoT, blockchain, Node.js that is actually running WebAssembly as well over V8, and so on. On the browser side, you have a bunch of applications that actually really leverage on WebAssembly. You can think of everything that is really intensive in computation, like video, audio, image processing, this kind of stuff, video game, and also complex web apps, like Google Earth, for example. To give you a quick history, Google Earth before was only available on Chrome because it was using something called native client that was like a precursor of WebAssembly. But since they switched back, they evolved into WebAssembly, it's now possible for you to run Google Earth in whatever web browser that supports WebAssembly. So in this talk, we're going to mainly focus on this part. That means providing a WebAssembly module to the target that will be the virtual machine. And our final goal will be ideally to find bugs in all those different stages. So that's what we're going to do. And my goal is to show you how you can basically improve your fuzzing process over time to basically reach more in-depth code paths into the WebAssembly VM. So the first technique I used was coverage-guided fuzzing. It's pretty easy. The main reason for that is since the first stage is actually the decoding of a binary, coverage-guided fuzzing is actually suiting pretty well. So the main goal for us will be to provide a corpora, so the corpus that will contain WebAssembly module, basically. We're going to provide that to a fuzzer. The fuzzer will do the mutation, meaning that it will add randomness into the WebAssembly binary, and then it will provide that to the WebAssembly VM. At the same time, we are monitoring the coverage, so we monitor how deep and how interesting this sample is, and based on that, we will either classify that as an interesting sample. If we get a crash, we are keeping the crash on one side, and so on. So it's basically the way it works. So for the input, I mentioned it's a WebAssembly binary format, so it's not that complicated. If you take a look at the structure, you have one header that is composed of one magic number plus a version. So the magic number is a null byte ASM. And then you have 11 sections that are unique and one custom section that can be in an unlimited amount of time. So the first target I fuzzed was basically a bunch of standalone VM and parsing libraries, so mainly written in C and C++. The main reason for that is I was working a lot on reversing and analysis of WebAssembly modules, so I was using those tools, and I decided that it could be a good shot to actually fuzz them at the same time. So I target basically binarium, WebIT, WASM3, and some other, and even RADARray2, since I was using that for reversing as well. So nothing complicated. I mean, I will not focus too much on that. That's the classical stuff if you are doing fuzzing. Coverage-guided fuzzing, I've used AFL, OncFuzz, and AFL++. My favorite is actually OncFuzz, but AFL++ is definitely a good contender. And after running a bunch of stuff and just basically instrumenting the target using the custom version the custom GCC or Clang of Fuzz or AFL, I was able to basically make the stuff to run and already start to find some crashes. So it was really easy, not that complicated, so that's the good part. The actually most complicated part is actually to do the triaging because I was triggering a lot of different bugs. So I report a bunch of them already, and as you can see, the most common bugs that we actually found was out of bound, some assertion error, a null pointer deref, and so on. So that was the common bugs at this stage, that is, in that case, the parsing of the WebAssembly module. So the first improvement I've made in my fuzzing strategy was basically to reuse the corpora between all targets. The main reason of that is since all those targets are written differently, they follow the same specification, but the implementation is different. So there is a clear real value of reusing one corpora to another, because what one tool will do in terms of the CFG and so on, and the different checks it will do, might not be the same than another one. So it was the first step, and then the second step was also to add all the crashes that I found on one sample directly into the global corpora that I was using. Again, the main reason is it might be a crash for one program, but it could be a really interesting sample for another one. So there is no reason I'm not doing that. Then I decided to do in-process fuzzing. So in-process fuzzing is basically, let's say, optimized way to do fuzzing. The main goal is basically you will get your fuzzer that will actually run your target in the same process, so it will be way faster. And in that case, you don't need to restart the process. You can just, for every test cases, replace them in memory and provide that to your target, and so on and so on. So it's way faster. The main reason I've been doing that only on Rust and Python is since I was already playing with C and C++ and finding bugs, it was not worth it at the time to basically create fuzzing harnesses for them. It was already working well. I mean, I was happy with the result, so I decided that it was the good shot to actually target something else and basically try some other tools. So in that case, I fuzzed the standalone VM and parsing library mainly on Rust. So you can think of Wasmer, WasmTime, WasmParser, and so on. So this kind of WebAssembly runtime and standalone VM. And I also target two other tools that I was using, like PyWasm, that is a Python interpreter, and WebAssembly.js, that is a JavaScript library for WebAssembly in general. So the result of that, when you are doing in-process fuzzing on Rust, you have a bunch of tools that are available. The funny part is actually those tools are binding to the classical C and C++ tool. So if you are already familiar with them, it should be pretty easy for you to basically ramp up into Rust in-process fuzzing. So I was using Cargo Fuzz, Fuzz Rust, and AFL Rust. And the main part in that case is to write the fuzzing harness. So with some luck, the documentation is pretty good, but even in that case, I mean, Rust is not that complicated to read, so you can, it's pretty straightforward, and most of the time, the name of the function are pretty clear of what it's doing. So I've made that for basically all the target I was mentioning previously, so a bunch of fuzzing harness, and then I was running the stuff. So it was not that complex. What you just need to write the fuzzing harness, learn a bit how to play with the framework, and you are good to go. For Python and JS, I was using Ateris. So it's a Python fuzzing framework. It's actually based on libfuzzer and GSFuzz. So again, you just need to write the fuzzing harness. So you don't need to know exactly how the language works and be an expert in development and this language. You follow what the like fuzzing harness template, and then you are more or less good to go. So the result of that was like 62 bugs, mainly on Rust, actually. And the type of bug I actually found was panicking macros, index out of bound, unwrapping, overflows, and so on. So just to mention, we say that Rust is memory safe. That's true, but it doesn't mean there is no vulnerability. Typically, this one, in the context of a CLI application, it's not critical. But if you are using that in a library on a server and you are able to trigger a panic in Rust, that means you are crashing the server. And for blockchain software, in the same way, you are crashing the whole network, or at least the node. So that's clearly critical, and that's really important to have that in mind. So the improvement I made at this point was basically to improve my corpora. I was reaching a point where actually the coverage was not evolving that much. So I basically took a look at the official test suite of WebAssembly and also at some existing fuzzing corpora that was available on GitHub, and I add that to my corpus. Again, the main goal is I maybe have one specific binary that will actually contain a dedicated feature on WebAssembly that I was not aware of, and it's maybe worth it to put it in place. Then we are going to the validation phase. So I've been fuzzing a lot the decoding part, finding a lot of bugs, but then I reached the point where basically my WebAssembly module was correct in terms of the structure, the binary structure, but in terms of the content, there was invalid. So the first step, of course, is to add some new fuzzing harnesses dedicated to first those entry points that are the validation function. And then I decide to also take a look a bit more at the validation mechanism to learn a bit more which kind of stuff was actually checked at this point. So there is a bunch of stuff like the type, especially the type, and the kind of opcode and how they interact to each other. So there is a huge work on that, and it's really interesting to learn more from this stuff. So for the grammar-based fuzzing, usually we are writing a grammar and so on. So I've used grammar-based fuzzing in a bit different way. In that case, my goal, since we have the WebAssembly text format available, that is called the WAT, I decided to grab all the WAT files that I was able to find, and using some tool to basically convert this text format into WebAssembly module. So that's the good part with these specifications that have been designed like that in mind at the beginning. You can go from a WAT file, the text format that is on the right, easily to the binary format and so on. So we can also, and that's been for us for debugging and even to write some edge cases, use this text format representation. So it looks like that. It's not that complicated. You have the next S expression like to basically define the module section and so on. And then you have a linear representation that will contain the function body and the low-level instruction. So it's pretty easy to read, to be honest. I mean, if you want to do reversing on that, it's definitely not that complicated if you are doing a bit of reversing. In terms of the MVP instruction set, it was not that big. The data types are pretty limited. It's basically integers. You have some control flow operator. That's why it's a Turing-complete instruction set. You have some memory operators to load and store from the memory, some local and global variable, some arithmetic operators, constant, and also some conversion operators that basically allow you to switch from, let's say, float 32 to integer 64. So when I say that actually the instruction set is not that complicated, that's why. For example, for the integer 32 and the integer 64, that's basically the exact same opcode, it's just that it's specific for one format or another. So there is, let's say, already half the stuff that are actually pretty redundant and easy to understand. So by doing that, I actually found some vulnerability, more or less by accident, because when I was converting those WAT file into WebAssembly module, I was at the same time doing some fuzzing, because why not, and actually found some bugs inside. So it was mainly assertion failure and one out-of-bound memory error, so not that interesting, and especially even the tools are not supposed to be run into a server and so on. So even the impact was not that interesting. But I mean, that's still some free bugs, so why not? So the strategy improvement I've made in that case was since I was aware of the text format and the internal structure, I decided to try to write some edge cases about that. Typically, I mentioned there is some section, and the sections are unique. So what is happening basically if you try to duplicate the unique one and the custom one? I tried to change the ordering to see if some tools are actually dependent of that, and so on and so on. I even create a polyglot WebAssembly module that is at the same time a valid HTML file and a valid WebAssembly module, just for fun. But actually, I didn't think I found any bugs with that. But at least it was funny. So it was the first step. I got even more stuff in my corpora, that's good, but it's still not enough. I mean, when I'm fuzzing in that case at this moment, that means I will be stuck. I will always go to the decoding phases and then going to the validation phases. So what I decide to use is structure-aware fuzzing, where basically I will directly, since I have knowledge of the WebAssembly module structure internally, I will be able to generate valid WebAssembly module directly from scratch inside my fuzzer. So it's really good. I will not lose time in parsing, so it will still go in the parsing phase. But what I mean by that is instead of sending, let's say, 100 files into the process and maybe 50 of them are rejected for invalid format, in that case, 100% of them will actually go through the validation phases. So that was really efficient in that way. So the way I've used that is basically by leveraging on, in Rust, what we call the arbitrary trait. So you basically have already a bunch of tools that you saw in Rust that actually define a WebAssembly module structure. So by using the arbitrary trait, I'm forcing basically my fuzzer to try to fill this structure by random byte to get something valid. In the same way, you have Wasm Smith that is actually even better. That was released a bit after I was doing that. And typically, this WebAssembly test case generator will generate WebAssembly modules that are always valid at the same time. So I retarget all my stuff by doing in-process fuzzing for at least the Rust libraries. And at the end, I also target the other one, since the corpora was actually shared between each other. So that's also the good part. So it was not that complicated. Again, you just need to do a bunch of Rust. In that case, arbitrary trait can be a bit challenging, but that's OK. So I found 0 new bugs directly using that. But the fact is, since the new stuff was generated and put directly in the corpora, I don't monitor exactly which new bugs, what are the input files that actually triggered these bugs after mutation. So I might actually have found some bugs using this technique, but I don't know. So at least it increased the coverage, since I was filling my corpora with only valid WebAssembly modules that are interesting. So at the end, we have the instantiation and the invocation. And in that case, I decided to use differential fuzzing. So that could look weird, because differential fuzzing is not something that is really common, to be honest. So first of all, I create some new fuzzing harnesses to actually instantiate my module. And then I decide to basically implement differential fuzzing using some really simple script. So the goal of differential fuzzing in that case is you're going to provide a WebAssembly module to your different targets, and you're going to monitor the result. It could be really simple, like monitoring the return code, or it could be more complex, like checking the exact return value. So by doing that, my goal is really to identify for one given WebAssembly module what are the results of all the different targets I have, and if some of them are actually rejecting the module or validating the module, and it's different than the other, that means something wrong is happening. So differential fuzzing is for me the really maybe most efficient technique to find logic bugs. The downside is, of course, you need to have multiple implementation of the same target or maybe different version of the same target. That's usually what we have with like regression testing. That's exactly what we are doing, and so on. So some famous differential fuzzing projects, you have, for example, CryptoFuzz, and the goal is to find cryptographic vulnerability in the different implementation. So it's done by Guido van Kreen. And another one is Beacon Fuzz, that is another project of mine, and it was basically fuzzing Ethereum 2.0 validation client by doing differential fuzzing. Again, the same goal, finding logic bugs. So logic bugs can look not so appealing, to be honest. It's always depending of the context and who are running the WebAssembly module. Typically, what you will have most of the time are unimplemented features, especially on WebAssembly. So it will require you a lot of debugging and manual analysis to determine if there is no false positive. So that's the downside. But on the other way, if we are going in the context of blockchains, a logic bug like this one, meaning you are providing a WebAssembly module as a smart contract and it will be executed and so on, and the result can be different between clients, that's typically the sign of a consensus bug, so it's really, really critical. I mean, it's one of the most critical vulnerabilities you can have in blockchain software in general. So for the fuzzer, nothing that complicated, just a Python script or a Bash script is enough. I've used Rust as well. You can basically target all the different, I was targeting all the different targets I implemented because, I already got all the fuzzing harness, so it was really easy for that. So it was not that complicated, but again, it requires a lot of manual analysis to determine if yes or not you have some vulnerability. So I found 2 bugs in WebIT, that is one of the most used library written in C, and in that case, yeah, it was incorrect validation or rejection of WebAssembly module. But what about browsers? Because since the beginning, I'm speaking heavily more on standalone VM. So let's talk quickly about browsers and actually the stuff that they got that is a bit more special. So typically, WebAssembly, the WebAssembly VM is part of the JavaScript engine, and so it's directly inside SpiderMonkey, JavaScript Core, or V8 for the most famous one. And we have multiple stuff that are actually involve the WebAssembly. Of course, you have the WebAssembly runtime, that is exactly the same as what I've shown you. And then you also have the JavaScript interrupt. That means that's all those WebAssembly API that allow you to communicate from JavaScript to the WebAssembly VM. So for this one, there is plenty of them. Actually, the MDM is really a good documentation for that. And using those JavaScript API, you are able to basically instantiate a WebAssembly module. You can create some memory, some global, some tables. So all the stuff I told you that was basically shared between the host and the WebAssembly instance. And we are doing something like that. So when you are dealing with JavaScript code, in that case, doing something like coverage-guided fuzzing is not that easy, and especially if you want to mutate your input file, you will need to deal with JavaScript syntax. So definitely not the best. So for that, usually I'm using grammar-based fuzzing. So that's what I've done. The only downside is you will need to write the grammar, so it could be time-consuming, but the WebAssembly APIs are not that huge. So that's what I've done with Dharma and Domato, and those tools will basically generate some sequence of WebAssembly JavaScript API, like the one on the bottom. And after that, I will provide this JavaScript file directly to the JS engine, and it will basically create some object and target this extra new part of the engine that we have, that is the JavaScript interrupt and also the WebAssembly runtime by effect. I've also used a really good tool named Fuzzily for Wasm. It's basically Fuzzily with some patch to add WebAssembly on it. So that's what you have on the top right. It's actually generating some really good stuff, and it was working pretty well. So at the end, it was long but not that complex to create those grammar, and it actually triggers some bugs that in that case are not public or duplicates on some other one. So that's working well. Usually when I'm teaching browser fuzzing, I always invite people to actually use grammar-based fuzzing for that. It's also a really good way for you to learn more about your target, because you will need basically to implement all the spec on that. So that's the good point. So that's the WebAssembly VM. The fact is, since we are running inside a browser, there is what we call also the WebAssembly JIT engines. So usually the classical way is, let's say for JavaScript, you have your JavaScript, it will be parsed into AST, it will be converted into bytecode, and it will be interpreted. After some time, when the code will be hot, it will go through the JIT engine, and you will get like an optimized machine code that will be executed each time you are calling the function. So the fact is, they actually implement the same concept for WebAssembly. So when you are providing a WebAssembly module, the first time it will be interpreted, so nothing fancy in that case. And if it becomes hot, it will go through the JIT compilers and be optimized, generate machine code, and be executed as well. So for SpiderMonkey, we have like a 3-tier compilers, JavaScript core as well, and for V8, we have Liftoff and Turbofan that are the ones that are used. So the main goal for me with, in that case, differential fuzzing against the JIT engine is basically to reproduce a concept and a technique that is already used for classical JavaScript. That is, we have a function. We are calling this function with some argument. We are getting a result. Then we force the optimization by the compilers, and we are calling again the function. What we hope to find is basically a difference between the interpretation and the compilation result. And typically, those kind of stuff lead to incorrect optimization. So that's the good part. The fact is, since we also have WebAssembly compilers, we can perfectly apply the exact same technique for WebAssembly. And in that case, I will generate a WebAssembly module that will do some operation. I will load that using JavaScript. I will call this function, call this module. This module, by default, will be optimized by Liftoff, and I will force the optimization in order to make Turbofan to optimize the WebAssembly module and this particular function. The main goal, again, let's say that you provide an argument to a function. The goal is to find for the same argument 2 different results on that. So that's a technique that actually is working well. It's actually not that complicated to do, but the downside is you need to generate valid WebAssembly module, and especially valid WebAssembly module that contain interesting bytecode inside. So that's what you can see on the upper right is basically the code generated by Liftoff, so it's a pure assembly. And then you can see on the bottom the code generated by Turbofan. So the way it will go from one to the other is by doing a lot of optimization on the bytecode and leveraging on a bunch of profiling data that he actually retrieved at runtime. Yeah, again, the goal is this one is the one on the right, and the one at the bottom is actually doing the same stuff. That's the goal we want to find out. So for the moment, no bugs found with that. It's actually a recent stuff I've made. For all the rest of the research, it was basically taking me a bunch of months and years to do over all this process over the time, and basically also adapt all my toolings to the modification in WebAssembly. So this one is still in progress. I will let you know if I'm finding any bugs on that. The fact is, I have not, so there is some public research about JIT engine fuzzing and vulnerability research in like incorrect optimization and so on. Really a bunch of research done by Samuel from Project Zero and Amy from Red 2 System and so on. But on the WebAssembly side, I have not seen a lot of stuff actually. So if someone is doing something similar, please come to see me at the end. I will be really happy to discuss that. So the final result of all this journey is basically something like 120 bugs, more or less. Some of them I maybe just forget. The final corpora size is like 2 million WebAssembly modules. So as I mentioned, the fact that I'm storing everything between all those different tools, targeting something like more than 20, 30 targets, it's just starting to be a really huge corpora. The good part is when you have something like that, if there is a new tool that comes in the wild and that is actually parsing WebAssembly binary, I can just take all my corpora, doing corpus minimization on it, and I will get something that will reach a huge part of the coverage for free. So it took me around 2 years, not full time, of course. I would say maybe 6 months full time to do all of it. Something like 84 fuzzing harnesses, more or less. I actually released an open source tool, WebAssembly runtime fuzzing. I released it maybe two years ago, so it might need to be updated, but it's in progress. The interesting stuff we can see is that actually coverage-guided fuzzing and in-process fuzzing that we can consider are actually using similar technique, but just one is faster than the other one, is the stuff that actually find the most bugs. That's always showing that it should be a default stuff to be done by the developer, because it was clearly not difficult to implement that, so there is no valid reason for you to not put any fuzzing and coverage-guided fuzzing in your CI, especially because you basically have fuzzing framework for all the language that exist, more or less. So that was nice. The challenge is it's complicated to update everything. I mean, all the different targets evolved, and I have a full-time job, so and it's not that. That's why. Also, the fact that there is a different WebAssembly features is an issue, especially for differential fuzzing, as I mentioned, because one might support it and not the other one. And then you also need to adapt to multiple fuzzing framework. So that's actually the good part. I mean, it's a nice excuse to basically try to fuzz everything and so on. So some future and next step. I'm planning actually to implement and fuzz like the Go. There is some tool, some WebAssembly VM written in Go, so I'm planning to fuzz this one as well. Maybe some Java one. There will be some implementation as well. And also, since recently they announced WebAssembly MVP 2.0, I'm also planning to basically update my fuzzing harnesses and maybe find some new bugs in those new features that will be added into. So I hope you learn a lot and that my journey into fuzzing can help you to basically copy-paste this journey but just change the target. And please let me know if you are doing fuzzing and you want to discuss more about that. I mean, you have my Twitter and I'm pretty responsive. So thank you.